Hello, everyone, and welcome back. So, in the previous lesson, we talked at some length about conservative vector fields and their associated potential functions and how to calculate a potential function for a conservative vector field. And in today's lesson, we're going to be talking about how we can use that potential function to help us to calculate line integrals of conservative vector fields very efficiently. So here is the theorem that we will be using, which is called the fundamental theorem of line integrals. And the setting is that we have some curve C, and let's call the initial point of the curve A, and the final point of the curve point B. And we have some vector field called F, which we know is conservative. And we talked yesterday, if your vector field is conservative, it definitely has a potential function out there somewhere. So let's go ahead and call that potential function lowercase f, as is tradition. If you're in a situation like this one, working with a conservative vector field, and you're trying to find the line integral of that conservative vector field over that curve, all you have to do is take your potential function, plug in the terminal point of the curve, plug in the initial point of the curve, and then subtract the two results. So I feel like this theorem is very similar in spirit to the fundamental theorem of calculus, which you learned in Calc 2. Which said that if you were integrating a function, g of x, from some initial value x equals a to some final value x equals b, then all you had to do was find an antiderivative of the function that you were integrating, and then plug in the final x value, plug in the initial x value, and then subtract the two, where capital G is an antiderivative of lowercase g in this context. Step number one, find an antiderivative. Step number two, plug the limits into the antiderivative. And step number three, subtract the two results. The fundamental theorem of line integrals is very, very similar. Instead of finding an antiderivative of the function that you're integrating, you're finding a potential function for your conservative vector field. And then you plug in the two endpoints of your curve and then evaluate and then just subtract the two results. So basically, this is the fundamental theorem of calculus for line integrals instead. So let me give you an example of this theorem as used in practice. We have the curve C, and this is the line segment from the point 2, 0 to the point 0, minus 3. We let f be the conservative vector field x comma y that we've worked with a few times up to this point. And someone says, calculate the integral over C of this vector field. So the first thing that I would do in a situation like this, if I didn't already know, I would check slash confirm the vector field that I am working with is conservative. We could call this in some sense step one. So as usual, I would check this by calculating the curl of the vector field, using in this case the formula for two-dimensional curl. And I would confirm that the result of that curl is always equal to 0, and that is indeed true. Now, once I have confirmed that my vector field is conservative, I recognize that I am now entitled to calculate the line integral using this formula and using this theorem. Because my vector field has been confirmed to be conservative, I can calculate this line integral simply by finding a potential function for the line integral, plugging in the two endpoints of my curve, and then subtracting the two results. Now, to use the fundamental theorem of line integrals, I need to have access to this potential function, lowercase f, that appears on the right side of the formula. So step number 2 in the process of calculating this line integral using this method is to go ahead and find that potential function for the vector field. So I will use exactly the same process that we saw in our examples yesterday. I'll take my vector field and I'll take its x component and I will recover the potential function by integrating with respect to x. And from this, I get x squared over 2 plus potentially some hidden terms that do not contain any x's and only contain y. Meanwhile, the potential function is also equal to what we get if we take the y component of our vector field and take its partial antiderivative with respect to y. So from that we get y squared over 2, and then potentially some terms that don't contain y at all that are hidden right now. Now, if I look at the information that's been revealed by both of these representations of the potential function, and if I put those together, it looks like our potential function is going to contain x squared over 2 as revealed by the first integral and y squared over 2 as revealed by the second integral. So this would be the potential function for the conservative vector field in this problem. This would be the function which my theorem calls lowercase f, that's being used on the right side of this equation. Now, to finish calculating the line integral using this theorem, the final step, step 3, is plug the endpoints of C, of my path, of my curve, into my potential function, and then evaluate what I get from that plugging in, and then subtract the results. So let's go back to the question and let's look at what they told me about my curve C. Curve C was said to be the line segment that stretches from 0 to 0 to the point 0, -3. So the initial point of this curve, my point A, would be 2, 0. And then the final point of this curve, the terminal point, would be this 0, 3 from the question. So if I evaluate f at the terminal point B, then I'm evaluating f at the point 0, -3, and I will go ahead and evaluate that by plugging those inputs into the formula for the potential function that we found in the second step. So x is 0, giving me 0 squared over 2. Y is -3, giving me -3 squared over 2. And therefore, the output of the potential function at the terminal point of this curve is just equal to 9 over 2. If I do the same thing with the initial point along the curve, f evaluated at A, f evaluated at the curve's first position, which is 2, 0, then I would plug this x value and this y value into my potential function, which would give me 2 squared over 2 plus 0 squared over 2, result 2, I think. Finally, to finish the calculation of the line integral of this vector field, all I have to do is subtract the values of the potential function at B and the potential function at A, and I get 9 over 2 minus 2, which I think is 5/2. 5/2 is the value of this line integral. 5/2 is the same result that I would get if I calculated the value of this line integral using the original formula that we introduced a couple of lessons ago. If you did parameterize this line segment and plugged the parameterization into the vector field and found the derivative and the dot product and the et cetera, if you did that process, you would get this same answer of 5 over 2 for the line integral. But the fundamental theorem simply affords us a different technique for calculating line integrals when we are dealing with specifically conservative vector fields, which have a potential function. I do want to emphasize that this theorem can only be used when working with conservative vector fields, because these are the only vector fields that have this potential function, lowercase f, in the first place. If you try this process for a vector field that's not conservative, what you're going to see is that when you try and find the potential function, the two representations of lowercase f will be irreconcilably different. So to give you a quick example of what can sort of go wrong, if you're trying to do this process with a vector field that's not conservative, let me show you this example here, which is the vector field negative y comma x. So let me put this in red to indicate that the following work will not lead you to the correct answer. I am about to give you a demonstration of work that is not going to bear fruit in this particular problem. So, for example, the student decides, I'm just going to skip the step of checking to see if this vector field is conservative or not. And instead of actually manually checking that the vector field is conservative, they just assume that the vector field is conservative and attempt to find a potential function for this vector field. So they say, okay, I'm going to find my potential function by integrating the x component of the vector field with respect to x, and that gives me negative xy plus some terms that might not contain any x's, some invisible terms. Only terms containing x are visible in this first representation. So then they go ahead and find a second representation of the potential function by integrating the y component of the vector field with respect to y. And they get from that xy plus some terms that might not have any y's in it, that some terms that might be invisible because they don't have any y's in them. Now, the issue with this potential function that we're trying to find right now is that there is a mismatch, an irreconcilable mismatch between the two potential function representations here. And the problem is that this term containing both x and y in the first representation And this term containing both x and y in the second representation, these two terms are not an exact match to one another. And that's a big problem. The only difference between these two representations of the potential function should be that terms containing no x's are invisible in the first representation, and terms containing no y's are invisible in the second representation. But terms containing both x and y, like this one, should be visible and identical in both representations. If there is any mismatch at all in the two representations of your potential function, in these terms containing both x and y, that's a problem. That typically is a sign that your vector field was not actually conservative in the first place. So either you skipped the step of calculating the curl, or there was an error made when the curl is calculated. So having seen what can go wrong if you try to use the fundamental theorem on a vector field that might not actually be conservative, let's go back to this problem and talk about how to solve this problem the correct way. Here I have this vector field negative y comma x, and I'm asking for the line integral of this vector field over the line segment C that was given to me when this problem was first introduced. So what I should do first, the correct solution to this problem, is I should manually check if this vector field is conservative or not. So I'll go ahead and calculate the curl by taking the partial in the x direction of the second component, the partial in the y direction of the first component, and subtracting the two results. And I get 1 minus negative 1. I get a curl of positive 2, which is definitely non-zero. So what this is saying is that indeed this vector field given to you in this problem is not conservative. You will not be able to find a potential function for this vector field, which means that we cannot calculate this line integral using the fundamental theorem that we introduced at the start of this lesson. So in a situation like this, where you're asked to find a line integral of a vector field that is not conservative, you might have to find that line integral using the original method and the original formula that we introduced a couple of lessons ago. So we're going to have to use this method of starting by parameterizing C. C was said to be the line segment from the point 2, 0 to the point 0 minus 3. So I'll use our linear interpolation formula. I'll use our LERP formula to parameterize this line segment. And I'll say I will parameterize C using the vector valued function that is obtained by taking the vector pointing to the first location, the initial point, to 0, and scaling that by 1 minus t, and then adding t, scaling 0 minus 3, the final point of this parameterization. And this would be valid for t's between 0 and 1. 0 corresponding to this initial point and 1 corresponding to this final point. And then if we simplify this result by distributing and then combining the first components and the second components, it looks like what we get is 2 minus 2t in this first component from 2 times 1 minus t and 0 here in the back. And then the second component after simplification looks like negative 3t. So here is our parameterization for our line segment. Next, I'm going to take our vector field, which was negative yx, and I'm going to use the parameterization to express this in terms of t instead. And so I'm going to, everywhere there was a y, replace that by the y coordinate of the parameterization. Everywhere there was an x, I'm going to replace that with the x component of the parameterization. So negative y becomes negative 3t, and x becomes 2 minus 2t. So here is our vector field expressed in terms of the parameter t. Meanwhile, alongside that, I'm going to need to find the derivative of the parameterization with respect to t. I'm going to need to get these tangent vectors, so I can do that one component at a time. The derivative of 2 minus 2t with respect to t becomes negative 2. The derivative of negative 3t with respect to t becomes negative 3. Now I'll go ahead and find the dot product of the vector field and the tangent vector to measure how much those two quantities are aligned. So I have 3t times negative 2 from the two x components multiplied together. And then I have 2 minus 2t negative 3 from the two y components multiplied together. And I'll take those results and add them. Simplify that. And so it looks like our dot product is equal to the constant number 6. Finally, all that's left to do is to integrate the result of this dot product, starting from our initial t value to our final t value that we established when we set up the parameterization of the curve. For a line segment set up in this fashion, t going from 0 to 1. And now this integral is relatively straightforward. It would just be the constant 6 times the length of the interval of t's, which is just 6 in the end. So that would be the value of the line integral of this non-conservative vector field over this line segment C. So I've put these two examples back to back to showcase the difference in the method that we use to calculate line integrals based on the nature of the vector field we're given to work with. If your vector field is conservative because its curl is 0, then you can just find a potential function, plug in the endpoints of your curve, and then subtract the two results. If your vector field is not conservative because the curl is non-zero, then we have to go through this sort of older process of parameterizing the curve, plugging the parameterization into the vector field, finding the derivative of the parameterization, finding the dot product, and then integrating that dot product. Where a non-conservative vector field, we still have to use this older method. Let's do another example of calculating line integrals of vector fields using the fundamental theorem if we can. So here we have this vector field f equaling yz, comma, y plus xz, comma, z plus xy. And just as a reminder, this is the same vector field that we worked with in the previous lesson, which we saw was conservative, and this was the potential function. We calculated that in the previous lesson. Someone says if you have a curve C parameterized by this formula, go ahead and find the line integral of this vector field over the curve C. So I'm going to remind myself that we already showed that capital F was conservative with potential function what was it? Going back to the notes from the previous episode, it looks like it was xyz plus y squared over 2 plus z squared over 2. Because the vector field is conservative and has this potential function, we have unlocked the ability to calculate this line integral using the fundamental theorem. Which says that to calculate the line integral, all we have to do is plug the initial and the final points of the path into the potential function and then subtract those two results. So let's see if we can figure out from the information provided what is the initial point on this curve and what is the final point on this curve. Well, the initial point on this curve is going to be indicated by the parameterization at the initial and earliest time. So if I take the initial time for my parameterization, t equals 0, and I plug that into my parameterization, that should provide for me the initial location along the curve. So if I plug t equals 0 into this formula, it looks like I'm getting 0, 0, and then 15. Let's go ahead and find the terminal point, the final point along this path, what we call B in the theorem. And the final point would be indicated by the parameterization at the final time. So the final time here is t equals 10. And let me go ahead and plug 10 into this parameterization. So that becomes 10, t squared is 100, and then 2t plus 15 I think would be 35. So now let's plug the points indicated by our parameterization into our potential function to find what the theorem calls f of b and lowercase f of a. Lowercase f of b can be found by plugging the terminal point into our potential function. So xyz becomes 10, 100, 35. Y squared over 2 becomes 100 squared over 2. And z squared over 2 becomes 35 squared over 2. And then similarly, if I plug in the initial point of the curve into the potential function, then xyz becomes 0, 0, 15. Y squared over 2 becomes 0 squared over 2. And z squared over 2 becomes 15 squared over 2, using the x and the y and the z for the curve's initial location, achieved at this initial time. So with a little calculator help, I've gone ahead and cleaned up those two values to rewrite them as simplified fractions. And now to finish this question, to finish the calculation of the line integral, all I have to do is subtract these two results. Take the output of the potential function at the final point, subtract the output at the initial point, and if my math is correct, this looks like 81000 over 2, which is what? 40500, 40,500. Now, let's do part B of this question. In this case, we're still dealing with the same curve C described by this parameterization. However, the vector field has changed to something different. The vector field is now z, x, and y. So this is not the same as any of the vector fields that we studied yesterday. We're starting from scratch. So the first thing I need to do is check whether the vector field is conservative or not. So to that end, I'm going to go ahead and calculate the curl of the vector field. And since this is a three-dimensional field, I'll need to calculate the curl using this 3 by 3 matrix representing the cross product of the nabla vector and my vector field. So if I calculate that using the standard process for 3 by 3 matrix determinants, it looks like I get 1 minus 0. It looks like I get negative 0 minus 1 from this diagonal here, 0 from the derivative of y with respect to x, and then minus 1 from subtracting the derivative of z with respect to z. And then the final entry in this cross product would be from these diagonals. So the derivative of x with respect to x is 1, and the derivative of z with respect to y is 0. So it looks like our curl is positive 1 in every component, which means it's definitely not equal to the 0 vector. Honestly, I probably could have stopped this calculation basically right away. I found the whole curl vector, but to tell you the truth, I really didn't need to, right? As soon as I saw that there was even a single non-zero entry in the curl, it was over in terms of the vector field being conservative. For a three-dimensional vector field to be conservative, the entire curl vector has to be 0, right? So if you see a non-zero entry anywhere, you know right away this is a non-conservative vector field. As a result, the fundamental theorem of line integrals cannot be used. So I would have to calculate this line integral of this vector field using the original formula and the original method. So I would start, if necessary, by parameterizing the curve C. However, in this problem, I'm lucky because the parameterization was provided to me. So I'll just copy it down here. So then I will go ahead and take my vector field, which was z, x, y, if I remember correctly. Yep, z, x, y. And I'm going to replace this z and x and y with this x, this y, and this z. And if I do that, now my vector field is in terms of t alone, giving me 2t plus 15. X gets replaced by t, and y gets replaced by t squared. Now I need to find the tangent vector for this parameterization, the derivative of r of t, which I can find component-wise. T becomes 1, t squared becomes 2t, and 2t plus 15 becomes 2 after the derivative is taken. Now let's figure out how much the vector field and the tangent vector are aligned using the dot product. So I'll have 2t plus 15 times 1 plus t times 2t plus t squared times 2. And then I'll simplify that. And if my math is right, the simplified dot product is 2t squared, 4t squared plus 2t plus 15. And the only thing left to do is to integrate this dot product to measure the total amount of alignment over the whole curve between the vector field and these tangent vectors from the initial t value, which was 0, to the final t value, which was 10. So finding that t antiderivative and plugging in those t limits, it looks like I get something like 4/3 times 10 cubed plus 10 squared plus 15 times 10, which, if I've got that right, is 4750 over 3. That would be the value of the line integral of this non-conservative vector field over the curve C.